Hi everybody, today we see again 5 questions. First question is this: the unit vector normal to the surface x square plus y square minus z equal to 1 at the point 1, 1, 1. Okay, so we have to find unit vector normal to this surface x square plus y square minus z equal to 1 at the point 1, x equal to 1, y equal to 1 and z equal to 1. So a vector normal to the surface, here x square plus y square minus z equal to 1. So I can take the 1 to the left hand side. So I have x square plus y square minus z minus 1 equal to 0. So this is the function of x, y, z, that is equal to 0. So f of x, y, z equal to 0 is this. So vector normal to the surface is given by the gradient of that function, the gradient del f. So this is dou by dou xi, dou by dou yj, dou by dou zk, and the function is this x square plus y square minus z minus 1, and we take the del f. Okay, so partial derivative with respect to x, that will give 2x, partial derivative with respect to y, 2y, and here minus 1. So del f is this. So unit vector, so this is a vector normal to the surface. If you have to find unit vector, we have to normalize this del f by magnitude of del f. Magnitude of del f is root of 2 square plus 2 square plus 1 square. Okay, that is root 9, that is 3. So in this option D is the correct answer. Okay, now another question is identify the correct statement for the following vectors: a 3i plus 2j, b I plus 2j. Options given are the vectors a and b are linearly independent, the vectors a and b are linearly dependent, the vectors are orthogonal, the vectors a and b are normalized. We can see the option D is wrong. The vectors a and b are not normalized, because here we see the magnitude of this vector is not 1. Here also the magnitude of the vector is not 1, so it is not normalized. The vectors are not orthogonal. If I take a dot b is not equal to 0, so vectors are not orthogonal. Then we have to check whether they are linearly independent and linearly dependent. Okay, we have to check whether the vectors are linearly independent or dependent. If two vectors are linearly dependent, then c1 plus a plus c2b equal to 0. This will be satisfied only for c1 and c2 equal to 0. For no other values this will be satisfied. Okay. So both the constants are 0. Only when both c1 and c2 are 0, this will be satisfied. Otherwise they are linearly dependent. Okay. So suppose they are linearly dependent. That means for non-zero values of c1 and c2, this is satisfied. So what that means is a is equal to, I can write a as minus c2 by c1 b, c2 by c1 some value m, a plus mb equal to 0. So if this is satisfied, c2 by c1, that is non-zero values, so that ratio is m, so a plus mb equal to 0. If this is satisfied, a plus mb equal to 0 is satisfied, then they are linearly dependent. So I take a is this, a is 3i plus 2j, b is I plus 2j, and if they are linearly dependent, this will be 0. Okay, so I have 3 plus mi, 2 plus 2mj. So if this is 0, this has to be 0. 3 plus m 0, 2 plus 2m 0. So 3 plus m is equal to 0 for m equal to minus 3. But for m equal to minus 3, this will not be 0. This will be 0. 2 plus 2m is 0 when m equal to minus 1. But when m is minus 1, this will not be 0. So there is actually no solution for a single value of m. This is not equal to 0. So such an equation is not satisfied. A plus mb is not equal to 0. Okay, a plus mb, this will not be satisfied. So that means they are not linearly dependent, but they are linearly independent. So they are linearly independent. So that is what we get here. They are linearly independent. They are not linearly dependent. They are not orthogonal. They are not normalized. So answer is option A. Okay. So A is the correct option. Third question. We have a differential equation, dy by dx plus y tan x equal to cos x. Boundary condition are given. Y of 0 is 0, and what we have to find is y of pi by 3. Correct to 2 decimal places. So given equation, suppose we have an equation like this: dy by dx plus p of x y equal to q of x. Right? Then to solve this, first we find the integration factor, which is exponential integral p of x dx. Okay, then y into integration factor, that will be equal to integral q of x integration factor dx, integral of q of x integration factor dx plus a constant. So this is how we generally solve the equation like this. So here the integration factor is exponential integral tan x dx. Okay, so that will be, as we integrate this, integral tan x dx. Actually it has to be written as sin x by cos x. Anyway, you will get that as log secant x. Okay, log sec x. So here exponential log sec x is secant x. So this is the integration factor. So by this equation, I can write that as y secant x is equal to integral cos x secant x dx, the integration factor plus c. So as we integrate this, this is actually 1. So I will get x. Okay, so y secant x is equal to x plus c. And we have this y of 0 equal to 0. Okay, so y secant 0, that is equal to 0 plus c, and that is equal to 0. Okay, so that means c is equal to 0. I mean y is 0. Okay, y is 0 when x is 0. So here, as I put y equal to 0, I will get 0. So c is equal to 0. So the solution is this: y equal to, the c is 0, so y is equal to x over secant x. And if we put we have to find y of pi by 3. So if I put x equal to pi by 3 here, pi by 3, secant pi by 3, I will get y of pi by 3, which is 0.52, correct to 2 decimal places. Okay, the next one is, consider a linear differential equation dy by dx equal to xy. If y of 2, y is equal to 2 at x equal to 0, then the value of y at x equal to 2. 4 options are given. So we have to solve this linear differential equation dy by dx equal to xy. So here this is a straightforward equation. Dy, we can write this as dy by y equal to x dx. Okay, I rearrange this. dy by y is equal to x dx. So integral, as I integrate integral dy by y, that is equal to integral x dx plus c. So this will be log y plus x square by 2 plus c, and when y is equal to 2, x equal to 0. So this x0 means log 2 equal to c, or log y is x square by 2 plus log 2. Anyway, from this I can get y equal to 2 exponential x square by 2. Okay, so this is the solution, or this is the value of y. And if here I have to find the value of y at x equal to 2. So if I put x equal to 2, I will get y equal to 2 e to the power 2. Okay, 2 square by 2. So 2 e to the power 2. So option D is the correct answer. The last one, f is a constant vector and r is the position vector. Then the gradient of f dot r will be, okay, gradient of f dot r, this we have to determine. F is a constant vector and r is position vector. 4 options are given here. Since f is a constant vector, we write it in this form: f0i plus f0j plus f0k. Okay, where f0 is a constant. So this is a constant vector. Okay, so f0 is a constant and r is position vector, so it is xi plus yj plus zk. So what will be f dot r? If you take the scalar product of f and r, that will be equal to f0x plus f0y plus f0z. So this is f dot r. Okay, now I am taking the gradient of f dot r. Okay, del f dot r, and gradient is this. So as I take the partial derivative with respect to x, here I will get f0i, here I will get f0j, f0k. Okay, I am taking partial derivative. So basically that is f itself. Okay, that is f itself. So here the correct option is option B.